Hello, this is Coffee from Shell, and this is the first video in the Practical Crypto Lesson series. What we're going to be focusing on in these upcoming videos, is going to be applying cryptographic concepts to solve basic CTF problems, right? So we are not going to focus too much on the theory, and we're not going to dive deep into theoretical portions. As much as we can avoid it, we are going to do that, right? So the topics for today's discussion are: what exactly is cryptography, or basically what is the need of cryptography, encodings and ciphers, and XOR or XOR or exclusive OR, however you want to call it. Right. So what exactly is cryptography? I think most of us probably have an intuitive understanding of what cryptography is, and for the most part, we're not going to discuss what the academic definition of this term is, but for practical purposes, cryptography would refer to a process that hides, or in fact changes information, process that hides or transforms or changes information. I'm sorry for my terrible handwriting. Or changes information in a way that if a third party or somebody who is not supposed to look at the information looks at it, they do not understand what the original or the actual information is. So cryptography is basically protecting the privacy of users, or protecting the integrity of the messages. Not really integrity, but like what the actual message is. Cryptography prevents it from being seen. The confidentiality of the messages is what cryptography aims to protect for the most part. Right. So let's think of it in simpler terms. So, as an example, if this is A and this is B, right? In most books, you'll see these people as Alice and Bob, but A and B works just as fine. So, if A and B are communicating, and this is a third person, this is the hacker or the threat actor or the third party or the person that we do not want to see the communication in between Alice and Bob. Right, so these two people are communicating. Let's say they're sending letters to each other. So if they're not really doing any encryption or any encoding or anything enciphering to their messages, see, the contents of their message are going to look something like this. So the message is going to be out in the plain. It's going to be in plain English. So it's going to be, hello, Bob. Right. So if somehow C is able to find this letter, so when C opens the letter, everything is there, plain, for him to see, and he understands all of the information in the letter. Now, this is not an ideal situation, of course. So what we do instead is that we change the information that Alice and Bob are sending to each other in such a way that when C comes across it, all C understands is a bunch of gibberish. So if the message was hello, and it was somehow made in such a way that to C it looks something like hello, maybe something like this. So this does not really make any sense to C, right? This is just a bunch of symbols. These are just a bunch of symbols that C sees, and he does not really understand what they mean. This is basically what cryptography does. In fact, what we just saw, this weird thing, which was the original message was hello. So the original message is, in this realm, usually known as the plain text, right? You're going to see this term thrown around a lot. Plain text. Plain text is the message that you're trying to send, or that piece of information as it is. No changes, nothing. When enciphering or encoding or encryption processes are applied, what we get then is the ciphertext. All right. In this case, what C saw was the ciphertext. So maybe it goes something like, now I do not remember what it exactly was, but maybe C saw something like this, right? Yes, this was what it saw. This is a bunch of gibberish, but here, this is actually a kind of cipher, and this is quite easy to understand. So we're gonna do just that. We're gonna understand it. This is, see, if there are 5 letters in the original message, there are 5 letters in this ciphertext as well. So each letter, in a way, is being substituted by another symbol. substituted. I'm sorry, I forgot the spelling. Yeah, so each letter is being substituted by a symbol. So H is being substituted by this Z looking symbol. Then E is being substituted by this zeta looking symbol. I don't know what this epsilon, yes, epsilon looking symbol. Then these L's are being substituted each by this squiggly line, and O is being substituted by this I like symbol. So what we're doing basically is that we're taking each and every part of the message and we're substituting it with another symbol. Now this is our key, this table of substitution. So you do understand that for if A is sending out a message using this substitution, so A sends out hello, A sends out hello, right? It travels across, and this is enciphered, so it goes across to B looking like this. This is how it goes to B. Yeah, yeah. And then for B to understand this, B must know the substitution for each of the letters. If B is unaware of the fact how these letters are substituted, then to B, this is what B receives, and B does not understand the message unless B knows this table that we have right here. So this table then, for most purposes, is our key, right? Not exactly, this is not the exact definition of a key, but in our case, a key, this opens the lock that this message is. So this table is our key table, or you can think of it as the chart that we refer to encrypt or decrypt the message. So this is what substitution ciphers are. Substitution ciphers basically take each and every part of the information, or usually in our cases plain text, and then they substitution ciphers, right? Substitution ciphers take these things and substitution ciphers, right? What they do is that they take each part of the message or a certain part of the message, each part, smallest unit of the message, however they're divided, and then they replace or substitute it with another part that is basically gibberish to the onlooker. That is how they maintain their confidentiality. So as an example, let's do this as an example.